Now, when we do direct dynamics, we are looking to describe a motion of the real physical system in terms of the joint accelerations when a set of joint torques is applied to the manipulator. Okay. So, this we need when you want to do simulations essentially. So, I have all the physical models, the models of the motors, everything, components put together, and now I want to turn it on and I want to simulate. If I give this voltage, then how will it behave? If you give a voltage from the motor, you can find out what the torque is, and then you can feed it into the equations of the robot that we have written so far, and we want to know what will be the joint velocities and accelerations as a result of that. So, the statement goes like this. So, we start at T0, and at T0 we know the positions q T0 and the velocities q dot T0. The acceleration is not important because that is what we want to compute in the next steps. So, we want to know what will be the joint acceleration q double dot T, right. Now, I am also given the torque which is being applied as a function of time at the various joints and the possible end effector forces HET. Now, how will you know the end effector forces? If you have holding a mass in the end and you are moving it over a specified trajectory, you can simply write mass times acceleration, and then you can add the g gravity component on the mass, and then you will know the end effector forces. Okay. Or if it is connected to a spring or a virtual spring could be if it is actually in contact with the surface, then that surface has a compliance. So, you can use that model also. And you then want to find out how the system will behave. So, now the trick is, if we can find out q double dot T as function of time, then we can always integrate it and find out q dot T and qt. Okay, so, this is the whole problem, a mathematical statement of the problem, which is okay. And so, there are two approaches towards it. Okay, one is using the Lagrange formulation, and so we start by restating it. State at time Tk is known in terms of the position qtk and velocity q dot Tk. Okay. Now, the acceleration, if you take q dot Tk, now you can compute this. So, you remember the original form, what did I have? I had b times q double dot plus t prime, where t prime was given by this, is equal to tau. So, all I have done is I have moved this term t prime q dot over to this side, and I have multiplied by inverse of the B matrix which I had. So, that will give me q double dot. So, this is a very simple formulation. Okay. So, but for this, when I calculate this t prime matrix, I am using q and q double dot at the present value, at the present estimate of q and q dot, which is okay. Because when I start, if you look at the definition of this problem, when I am starting, I know q and I know q dot T0. I know that when I am starting. So, I know this at some instant, so I can calculate this matrix T prime. So, I can subtract it from the torques which I applied, because I know torque as a function of time which is being applied. I can form this, and then I have calculated the B matrix, which is just a function of q, which is known. So, I get an estimate of q double dot. So, once you have written this, robotics finishes. Okay. So, this is as far as robotics is concerned. The rest is using numerical integration, and that I have already showed you how to do it for the simple system. Okay. So, you just have to code that. So, you have to write this into the second program which I showed you. So, one program will simply say you just call ODE 45 or gear or some other ODE method. I showed you there are several ODE methods which are available in MATLAB. So, you use it, and in the other function in which you have to define the derivative which the ODE solver needs, in that you will go and code the whole robotics part of it, which is this. Okay. So, you take a time step delta t, well you can do fixed time step, you can do variable time steps, you can do automatic error control, error check, all of these are built into MATLAB routines, standard, there are lots of other libraries, MATLAB is not the only library. There are other libraries which are available, which will give you standard numerical integration codes. Okay, so you do not have to work very hard for it. I mean just go type on the net and you will find standard libraries, mathematical libraries. There is an old one called NAG which is still around, which is very well proven. So, that is not a big deal. So, big deal is writing these two equations. Well, it is not a big deal because it is there in lots of books also, but then working with these terms is not easy. So, then what you do is, so what will the routine do? So, if you know q double dot, then you can write that program which you wrote last time in MATLAB. So, output of that will be essentially you will update the state. So, you will get q dot at t k plus 1 and the position q at t k plus 1. So, the next time instant you will get these two values, you go back, you recompute your tau prime, you recompute your b, you invert the matrix again and you are in business. So, repeat again, repeat, keep on doing this until you go reach the time that you are interested in. So, this is the basic procedure, okay, and we will try doing this in the lab this week and next week. So, this is the Lagrange formulation where it is straightforward. When you use the Newton-Euler formulation, you, if you remember correctly, you never calculated the B matrix. So, you cannot use exactly the same method. So, what is done is, but it turns out that this is computationally more efficient and this is what you do. Okay. If you are given q and q dot, you find the torques in the Euler-Lagrange formulation with q double dot equal to 0. So, you assume that the joints are not accelerating and you do the forward propagation and you do the backward force propagation, okay, to find out all the torques. Okay. So, if you take g0 equal to 0, q dot equal to 0, qi dot equal to 1 and qj dot equal to 0 and you and this is for and you repeat this for I is equal not equal to j, right, then you can find the full column Bi of the matrix Bq. So, if you repeat this from 1 to n, you will get back, you can reconstruct the matrix Bq which you got from the Euler-Lagrange formulation. Okay. So, essentially, so if you have that, you can form Bq tau prime q q dot and then given tau you can again do the numerical integration using the same method. Okay. Now, where do you get this from? If you go back into this formulation, if q double dot is equal to 0, then in the Euler-Lagrange formulation the matrix Bq does not matter, right. So, that is this step. So, this step gives you q q dot, tau prime q q dot, and this step allows you to compute the matrix B. So, you are back to where you are in this page, you know the matrix B, you know the matrix tau prime. So, you are in business. Again you do the same Range-Kutta and you can back out your whole problem. You can then do the direct dynamics. Is this roughly clear? Only way you will get it clear is actually doing it. So, we will try doing that in the lab. So, next thing is interesting to know is how does this process scale, because obviously in the lab I will give you a 2-DOF or a 3-DOF system to work on, because then you can track it, you can see what is happening, you can get a little feel of the terms. If you go full 3D, then the terms become fairly complicated and then you are left nowhere. Well, the Newton-Euler formulation is computationally efficient because you compute specific terms, you do not compute everything and then for example, do not compute the full tensor, right, do not compute the full Christoffel symbols and then go back and combine them to form one term Bij. I mean that is too computationally more expensive. So, if you are using the any formulation, then if when you are doing direct dynamics, it is the order of n squared. So, if you go from 2 links to 4 links, your number of computations will go from will scale. 2 squared is 4 and 4 square is 16. So, it becomes 8 times, sorry, it becomes 4 times, not 8 times. However, the inverse dynamics is only scaled with n. So, if you go from 2 links to 4 links, you will only go double, not 4 times. Okay. So, this is, I mean, scales better when you do inverse dynamics, and it goes n squared when you compute direct dynamics. So, if you go to Professor Saha, he will tell you that, oh no, this is not n squared, it is n into n raised to the power 0.6 or something. So, those are the kind of differences that he can do. So, this need not be n squared, it can be, it is somewhere between n and n squared, depending on how efficiently you write the algorithms. So, there are issues, and since you are often talking about 6, this power matters. I mean, 6 raised to the power 2, well, is 36, and 6 raised to the power 1.5 will be how much? So, yeah, 18, yeah, 6 times root 6, yeah, somewhere there. So, it matters if you are very large robots, then, or very large number of links, if you have parallel robots which have got very large number of connections, then it becomes more of a problem. So, these are the issues. So, some people say that it really does not matter, do not worry about it, you have an n square algorithm, simply use it. Nowadays computers become very fast enough, and then things can happen. Now, the issue, one of the issues is that the Lagrange formulation can also be made computationally efficient, okay, through a recursive implementation. So, you make sure that only the terms which you need are being calculated, except that you have to reformulate it quite a bit. Okay. So, you again write the energy terms, and you kind of see, actually if you think on it carefully, it also goes the same way, right. You write all the energy terms first, and then you take the derivatives. So, you can do that whole thing recursively. So, there is a better method to do that, but in that formulation it does not even look like a Lagrange formulation in the end. So, it ends up basically that these two methods, they actually converge. I mean, they are not very different methods, though it looks like it at times. Okay. So, quick revision. So, this is using Euler-Lagrange, and so essentially there is this q double dot term which I want to compute. So, I take all these terms, move it over to the other side, and all these terms together, this, these three, this and this together I am calling tau prime, moved it over and then multiplied by B inverse, and I get q double dot. Okay. Now, the next thing is, in this equation if I have q double dot equal to 0, then I am just left with these terms, okay, and obviously tau. So, when I am doing Newton-Euler, that is what I am saying, for if you take q double dot equal to 0, then this whole problem is solved, right. So, in this equation if I put q double dot equal to 0, then I am just left with these terms. So, if you calculate the torque vector with that, that will essentially give me tau prime. Okay. Now, if you look at this matrix, so the B matrix is multiplied by these terms q1 double dot to qn double dot. What you do then is, if I say make one of these, suppose I make qn double dot equal to 1 and the rest zeros, so qj, suppose I take one of them, so and the rest are 0, then in this column B11 will get multiplied by say q11, and then I will get tau 1. In the next row B21 will get multiplied by q1 double dot, and I will get tau 2. So, if I do this torque calculation, so when I said q dot equal to 0 and qi double dot, when I said this equal to 0, I am cutting out this term goes to 0, this term goes to 0, this term goes to 0, I am ignoring the gravity terms, So, essentially I land up with this element and then this element and then this element when I calculate the torque with this parameter. So, if I make now q2 double dot equal to some value 1 and I calculate all the parameters, I will get the next column, then the next column, then the next column. So, then I get the whole B matrix, and once I have gotten it, I can use the same approach as I use for the Euler-Lagrange. Okay, so, this is just revision, and I have added just this matrix to the formulation. Now, when we did our trajectory control, we said that given these q values I want to go from here to there, I just spliced it up, interpolated in the middle, and I came out with a set of q values. I never asked can the actuator produce the torques, and we saw, for example, when we are doing the blending, that if I decrease the interval too much, then the acceleration goes very high. Now, if the acceleration goes very high, then we expect that somewhere or the other the force or the torque has to become large, otherwise we will not get the acceleration. So, force is mass times acceleration, torque is equal to angular moment of inertia times angular acceleration. So, either the torque or the force has to rise. So, we have to look at these issues of torque limits, that in the bandwidth in the motion is the torque limit being reached. That is one thing. The second thing is, it is not only the issue of what is the maximum torque, it is a question of how quickly the torque rises. Okay. So, what is the response speed? You have all done some controls. So, you understand that if you have a first order response, then the response speed is determined by tau, if it is second order response, then determined by omega. Okay. So, that is also an issue. You cannot go, like if I ask you, okay, go to my office, yes, you can go to my office, but if I say go to my office in the next second, you say sorry, can't do that. If you say okay, next 5 minutes, you say okay, that is okay. So, it is something very similar to that. So, and we will look at it in more detail when we do controls, but the issue here is to understand that there is this problem. So, just being able to do the trajectory is not enough. Okay. So, you people do Robocon, right. So, you do Robocon, you can say okay, I want to go from here to here, I want to move like this and I want to move like this. Can you actually do that with the actuator in that amount of time is the question. So, for example, if you have segments of high curvature, then you need kinematics based on that is interpolation segments of high curvature, then you need high dynamic performance for the manipulator, and then the torques could exceed. So, we are going to look at this case. So, we take a qt between 0 and Tf. So, I have a trajectory of some kind on 6 joints. So, q is a vector in this case. So, we can do inverse dynamics given qt. So, we have for each joint we have the data. So, we can do inverse dynamics and I will get the torque history. Then once I have done the torque history, I compute the torques with the torque limits and determine if the trajectory is actually possible. Okay, now it may not be possible. So, what do I do? Obviously, what I can do is I can generate another trajectory. I say okay, now let us increase the time that I am doing the whole motion in, and then hopefully I will reduce all the accelerations. I mean, you are doing the same motion in this larger amount of time, hopefully reduce all the accelerations. But now if I want to find out whether I have done things right, I will have to compute the torques again. Now, why do you have to compute it again? Because it does not scale linearly. So, there is velocity, there is q dependent term, there is q dot dependent term, there is q double dot dependent terms. So, when I am changing things, everything does not change linearly, right. I mean, it is not what you learnt in class 4. 6 apples do not cost twice what 3 apples cost. Okay, so, that is where you have a problem. Now, so what I am going to do in the next 15 minutes is a technique where I do not do inverse dynamics recompilation. I don't do compute it again. If I have done it once, then I can play around and I can change it. Okay. And not only that, I could also change things locally without recompiling the whole trajectory control issue. So it's just additional control which is there. It's like a flex band. So I can do it online, or I can do it very quickly. I can even write internally. So when you buy something like a Puma or a KUKA robot, right, you would think that why do you pay so much? Right, you pay 30 lakhs. The motor and the controller each will cost 2 lakhs. So 6, 12. What do you pay for the rest? So this is what you pay for. Okay, these kind of structures. Now, so we are going to simplify the manipulator dynamics. So I start ignoring friction, drag on the motors, because those are very nebulous things, not so easily manageable. I said, okay, I ignore the end effector forces, because the effect of that is you cannot change right now. So it's too nebulous. So now if you look at it, this term CQQ dot, it has quadratic dependence on joint velocities that we have seen, right. There is a Q dot before that and a Q dot after in all these equations. You just need to go back to your Euler-Lagrange and remember that there is a quadratic dependence, and there was the effect of the quadratic dependence that we had discussed. And so since it is dependent like that, so we split it up into a term which is TQ, right, and then a term involving this vector QQ dot. Now what are my Q's? They go from Q1 dot to Qn dot. Now if it's a quadratic, that means they get multiplied with each other. So what is the possible array of terms that I can have? I can have Q1 dot squared, I can have Q1 dot Q2 dot, I can have Q1 dot Q3 dot, I can have Q2 dot Q7 dot, and I can have, for each of this term I can have Q7 dot squared, and then I can have Qn dot squared. Okay. So in general this will be n into n plus 1 by 2 by one vector. Okay. So it's a vector this like this, n into, how many combinations can I make from n q dot terms? Essentially that many is in QQ dot. So this TQ matrix will become same, it will be n plus 1 by 2 and the other dimension will be n because Q is of order n. Okay. So I split it up into this form. So this is just some small mathematical manipulation that we are going to do to put it in a convenient form. So then we reformulate it. Now in this expression I have expanded this to write the T explicitly, because that is what I am going to operate on. So the same Euler-Lagrange equation rewritten in this form. So not much change here, and you look at this term TST, which represents the torque component that depended on velocity and acceleration. So terms like G, I say okay, I put it aside, it is not dependent on velocity and acceleration, it is dependent on Q. Okay. Now what we want to do is we want to scale the time factor. So that is why I want to write it as Qt. So we will now write a Q bar of RT, and such that Q of t is equal to Q bar RT. So that is a very simple operation. So I am just scaling it. So I am defining a new function, okay, such that Q of t is equal to Q bar of R of t. If R is equal to is just a constant thing, so R is t multiplied by 1, then it is the same thing. If it is t multiplied by 2, then I am crunching the time. Okay. Now by definition RT has to be a strictly increasing scalar function of time with R0 equal to 0 and RTF equal to TF bar. Okay. So I will just go one slide ahead and come back. So essentially if this is my t axis, and this is R of t, all I am saying is that it has to increase over time. So if you have a simple unity function, then it is the same, there is no change. Now, you can have a function like this which is always increasing with time, or you can have a function like this which is always increasing. So, this cannot come down, but it can almost go level and then it can increase again. So, it is always increasing, but locally you can change the slopes. Okay. So, the whole idea is that, I mean, just to give you a glimpse of what I am going to try to do is, see, somewhere out here it changes slowly compared to this function, right. So, if in this locality I had a large acceleration originally because I was moving fast, just in this small local area I can use a increasing function, always increasing, non-negative function, but locally I can change the slope so that I can reduce a local acceleration, I can reduce local velocities. So, that is the trick which we are going to play. Okay. So, once I have this, the rest is first year mathematics. So, you write q dot is equal to r dot q prime of r, okay, where prime denotes derivative with respect to r. Obviously, q double dot is r square q double prime r plus r double dot q prime of r. Plug it back in, you get r dot squared out here, and this tau q plus r double dot b q r. So, you get it in this format, just back substitution. This is not very interesting, but this is what happens. So, we had tau s of t is looking at just these components was this. So, I popped these out, r double dot. So, then I defined tau s of r as this term. Okay. And then simply tau s of t as this term. Okay. So, what we can then do is, we now have a relationship between the torque contribution depending on velocities and accelerations required by the manipulator for motions having the same path. So, I am just scaling time. So, it goes through the same path, but different timing laws with a catch, right. I am always going positive, always rising modification. So, I am not going back in time, okay, that is important, otherwise things will go for a toss. And I am simply scaling the time scaling the joint variables. Now, we have left out the gravitational torques because they are only a function of the joint position. So, I cannot work with them. When I go to a particular joint position, whatever is the gravitational torque component I will have. Okay. So, if I do time scaling, it is not changed, so I am not interested in it, I can't mess around with that. Okay. So, we know this formulation. Okay. So, I have popped out these terms. So, locally I have to play with, I have to modify r dot and r double dot to change the local accelerations. The simplest choice is to just do linear scaling. Okay. So, I am not doing, if I go back, so I am between here and here. So, I simply do linear scaling means I just go like this on a slant slope, or I go, well, there is no reason why I will go faster because all my torques will increase. So, that is the obvious choice. This is the more difficult thing to handle, but it can be done, okay, without, depending on what is the performance you require from the system. Okay, so, if you do that, then tau s tau becomes, now if you look at this carefully, if r t is equal to c t, then r double dot is 0. So, this set of term drops out. So, tau s of t is equal to r dot square tau s of r, and r dot square is c. So, it becomes c square tau s c t. So, if you change the time scale by c, it changes the magnitude of torques by c squared. Okay. So, this is the immediate thing which you should know. So, shorter time, at least those torques, forget the gravitational torque, if you take the combination of inertial, Coriolis and all these terms, it just increases by a factor of c squared if you reduce the time. And So, the time duration increases if you reduce this thing, and so and then there is the scaling factor which I am talking about by factor of c. It is a iteration of the whole thing. So, now what happens? Now, how do I apply this finally? So, what you do is you apply, you do the inverse dynamics, hopefully using recursive algorithm because it is simpler. You check whether torque exceeds the allowed limits during trajectory execution. We presume that your motors are strong enough to at least take care of the gravity load. Okay. Then identify the joint for which the torque has exceeded the limit, and which is the most has the severest violation. Okay. Then for that joint you find out a scaling factor c if you are doing linear scaling. So, essentially if you increase the time by a factor of 2, the other torque will come down by a factor of 4. You can't work with the gravity thing is wherever it is, that will not change. So, then you have a new time scaled trajectory, so it will not exceed the torque limit, so you are fine. The only catch is if you just do this linear thing, then you penalize the whole trajectory. You are slowing everything down over the whole domain, you are slowing every joint down. So, that may not be the best thing. Okay. You can definitely be smarter than that. Okay. For example, you can do these kind of modifications. This you have not increased time, but you have changed. So, you have reduced the slopes here. Okay. So, if you reduce the slopes here, then if you are getting the peak torque here, then you will be better off. So, similarly here it is even more local. So, in a local area where the torque is going up, you just change the slope locally and you are in business. So, these kind of modifications you can do, you can run nice optimization functions, okay, but for that you have to know optimal control theory, which we do not do. So, you have to do a master's here or a PhD here to learn these nice things, or somewhere else to do these nice things. So, we will kind of stop here at this application portion.